Yeah. I get so much subscribers.
So how's your new system setup working? Is it good? Is your new setup working well?
Well, that's what I'm testing. That's why I'm having like checking the sound.
Yeah, I'm also testing.
Okay, cool.
Okay, so trying to test a new recording thing. I don't think this works with the projector. Alright, let's start. Okay, so this is, apologies, I was trying for, some of you were saying that the slides were not very clear. I thought I would use a slightly different software to to record this, but I don't think it works very well. So I think it either records or it shows this. Does not seem to do both. Okay, so, alright, so okay, so let's continue. Hopefully, so Hong also has a new camera, so hopefully that will work better. So, alright.
This is backwards.
So
The screen
let's
is
see.
backwards.
Okay, so a couple of quick announcements.
Oh, it's just
So homework 5, I plan to post today. Okay, so I needed to cover a reasonable amount of linear programming before I could post this. So so you will see that. It will be due 2 weeks from tonight. Okay, so that's homework 5. And and as you guys probably saw on Canvas, the project midway report will be due next Friday. So this is more of a, as I was saying, this is like concretely writing down the details of what we guys discussed and trying to look at some data sets, trying to figure out which ones you will use. So that's the project midway report. Okay, so any questions on this? Some of you seem a bit concerned about what exactly will happen. Okay, right? So, okay, so good. So last class we were looking at linear programming, right? So you have a bunch of inequalities defining a feasible region. Okay, these were linear inequalities. And you had, and we denoted them by like A1 transpose X less than A1. N transpose X. Sorry, M transpose X. Where X is the vector X1 to Xn. And each of these AIs are also n-dimensional vectors. That's why you take dot product with X. And each one we said is a half space, and it's defined. So if you replace that inequality with an equality, then the object you get is a hyperplane. So this is what we said. Right, and what we said is we understood. Or rather, we covered quite a bit about the geometry of linear programs. Right, so we said what is a corner point. And a corner point is basically it's a point that is the intersection of n of these planes, n of the hyperplanes. And we also saw, suppose you have a corner point, what are the neighboring corner points in this polygon? Okay. So the other thing which maybe I mentioned last time but might be good to recap is that not all intersections of n of the planes are actually corner points because some of them may not be feasible at all. So this is the thing we saw. And then we saw how to get, given a corner point U and the bunch of planes that define this U, how do you get the neighboring point? So this we saw, and we said that the directions of the neighbors have a very clean formulation. Those are just the columns of this matrix A inverse, where A is the set of A is this matrix that contains all the planes that define U. Okay. So U is defined by a bunch of planes. You write down the matrix of whose columns are those things, and the inverse of that has columns that are these directions that go to the neighbor. So this is something we saw. And we also said that so you have this feasible set, and if moving to a neighbor does not yield an improvement in your objective, then we saw that this is actually the optimum. This is the idea behind the simplex analysis. That this is somewhat like this is local optimum in this moving to a neighbor sense means global optimum. We said that it's not exactly this because you only consider your neighbors. You move all the way. Alright. But the other thing was that the simplex algorithm is not polynomial time in general. So there are examples on which it can take exponential time. Okay, but it's still pretty useful in practice. But we said that you can solve, it turns out you can actually solve linear programs in polynomial time. And this is via what is called the ellipsoid algorithm. That was the first algorithm. And there are these other methods called interior point methods that also end up solving integral domain. Alright, so what we saw is, in some sense, how do you solve this continuous optimization problem given by linear constraints and linear objectives. Okay, so that's what we said. Now the question is, how do you use this for combinatorial problems? Right? So by combinatorial problems, I just mean things like matching and shortest paths, where all the formulations we wrote down had discrete domains. Right? So you wanted an edge to either be picked or it should not be picked. Right? So in some sense, how do you use these kind of continuous optimization methods to solve discrete problems? Okay, so that will be the goal of today. So the goal is using LP for combinatorial or discrete optimization. Okay, and let's start with this place where we always start, which is matching. Okay, so you have n vertices on both sides. We have a bipartite graph. So we keep calling them, let's say A U B. Right. So these are the sets of vertices, and you want to find a match. Right? So you want to find, and you're given a bunch of edges. And let's suppose I forget if in the previous class we called them Wij as the weights or Cij as the weights. Anyone know? Wij, right? So these are the weights. And we said that you can formulate this as an optimization problem where every edge is either picked or not. Okay, so you have variables x, I, j for edges I. Okay, so edge ij just means I over here is connected to j over there. Okay, so xij is either present or not, and this was supposed to be so for all I, sum over j in the neighbors I x I j is equal to 1. Okay, and you have the same constraints for the j, but I'm going to skip them, thinking of I and j as being small. Okay, so and same, yeah, maybe for clarity I should just write for all sum over I x. And your objective was to maximize sum over ij wij. Okay. So this is the maximum weight. So you are only summing the edges that were picked. That's the idea. All right. So this formulation is nice, except that this is not a linear program, right? Because these constraints are fine. They are equalities which are some special cases of inequalities. So each equality you can view it as it's like if you want A equals B, you can say A is less than equal to B and B is less than equal to B. Okay, so you can always write these as inequalities. That's fine. But what about those? Right? So you're saying that xij's have to be 0 or 1, and these are clearly not. These are clearly like discrete constraints. So what is a natural way to just make them linear constraints? What would be the first thing that comes to mind? Like suppose you had to make this a continuous optimization. Yeah. Yeah, so you can just say, each xij, so replace the constraint replaced with 0 less than equal to xij for all I. Okay, so this is the obvious thing you would want to do, to convert this discrete optimization problem to a continuous problem. Right? Because now xij can be any real numbers that satisfy this constraint and these two constraints, and you want to maximize. Now this is a linear program, and by what we saw in the previous couple of lectures, you can actually solve this what is called linear program in polynomial time. So, and you get some solution. So now, what is one difficulty you immediately run into if you do this? Either one.
How do you turn it back into an answer to your original question if you get some x equals to 3?
Yeah, so you get, right, so the main problem that you get is that, of course, right, so what if the solutions are fractions? Okay, so you solve this optimization problem where you are minimizing, you're maximizing this subject to those equality constraints and these inequalities. Okay, and maybe you ended up with a solution where xij, or let's say x1, 2 is 0.3. And the question is, how do you interpret this? Right? Can you convert? So the question now becomes, can you take a solution like this and somehow use it to come up with actually a true assignment? So that is one question you could ask. Another question you could ask is, would you ever actually get solutions like this? Okay, so that's the other thing you could ask. Okay. And we're going to see examples of problems today where we would be very fortunate and we would never end up with solutions of this kind. Okay? And one of such examples turns out to be magic. Okay? And in some sense, the question we will ask is, are these corner points integral? Okay? And so note that from what we saw last time, so these set of equalities and these inequalities, they define an object. It has some corner points, right? We said that if you optimize any linear function, the optimum is always achieved at a corner point. Okay? So suppose you could argue that all the corner points of this object all have only 0, 1 values. They don't have any fractional values. Okay? Then you would be in great shape, right? Because then you have proved that I can pretend that I just solve over this complete real numbers, but my solution is always going to be an integer point. Okay? It's actually going to be a true 0, 1 assignment. Okay? So you could hope that something like this happens, right? So if so, you would be in great shape. Okay? So it turns out for certain problems, one of them being matching, this is actually true. That you optimize over this continuous space, and this feasible set would be, it would be something that looks like this. Let's say, it turns out all these corner points would just be some 0, 1, 1. They would just have 0, 1 values. They would never have fractions. It's a very remarkable claim the first time you see it, because why should that happen? Right? Like alright, but first let's actually pause here for a little bit and see if you have any questions. Yeah?
So when we did this in class previously, well, I guess it just seems like one corner point to another feels like local search because you're treating like one constraint or another. But when we did that previously, we couldn't do that to be optimal in polynomial time. But then you're saying this again.
Oh no, so right. So the simplex algorithm is not polynomial time. But as I was saying, there are other algorithms that we did not see in class that actually do run in polynomial time. So yeah, So yeah, that's a good point. So what he's saying is the algorithm we saw in class, I said was not, so which was called the simplex algorithm. This is not, this does not have a polynomial time bound. But as I was saying, you can actually solve linear programs by other methods that don't work by going from a neighbor and searching around. Okay, so they go through the interior of the polygon, but eventually still end up at a corner because the optimum is always a corner. So these kind of algorithms do run in polynomial time. Okay, so you can assume from now on that I give you any linear program, you can solve it in polynomial. So, right. So now we are trying to ask, okay, so how do you now solve discrete optimization problems using that? So yeah, I mean you should think of linear programming as like a hammer. Okay, so you now have this powerful tool that can do linear optimization over linear constraints in polynomial time. Now the question we are asking is, can you use this hammer to solve some interesting problems? Okay. And the first problem we are trying to solve is matching. By luck, this thing, because often it helps to. So this is the claim that we want to say. All the corner points of this is called the matching polytope. Okay, so this is just set of feasible solutions. To the linear system that we wrote down. Let's give a name for this linear system. Okay, so this has, so we have these constraints. And so these are all the constraints. Okay, so let's give a name for this. Let's call it this. Out of a lack of any imagination, let's just call it star. So the linear. Okay. So these are a set of all feasible solutions. So here there will be some fractional stuff. Okay. But what we are saying is that all the corner points are actually all. And just again, so you have m variables. The m is the number of edges. And what is the number of constraints? How many constraints do we have? If you were just to count equality as just one constraint. This so that everybody's on the same. I mean, I've written down all the constraints. I'm just asking you how many. Sorry? Well, 3 kinds, yes. But how many are there? The first kind. Like let's take these. Right. So I said for every I you write down this constraint. How many I's are there?
And
So there are n I's, n things on the left, n things on the right. Okay. These are for the left, these are for the right. And so you have 2n plus the number of constraints of this kind. And how many are there here?
that would be just another n.
No, but now you have things for every edge, right? So for
it's-
every ij. So this would be m. Okay? So m is what we define as the number of edges. Okay? So you have 2 times n plus 2 times m constraints. So this is always a sanity check you should be doing. Okay, so it's like how many constraints do you have, how many variables you have, so that you have some sense of what's going on in this linear wanted. Alright, so these guys are equalities, and these are equal. Alright, so, yeah, any question? Okay. Okay, so these are what we have. And now I want to I want to show you how you would show a theorem like this, right? So you want to show that you have this object that's defined by these many constraints, and this is in m-dimensional space because m is a number of variables. And you want to show that every corner point, which maybe is defined by, so in this case we have m variables. Therefore, every corner point is defined by precisely m linearly independent equations. Because you want to solve. You have m variables, and the number of equations you need to solve uniquely is exactly m. So this is why we should be looking at m of these constraints, and we should be arguing about how they intersect. Okay. So this theorem is equivalent to showing that if you take any m of the 2 times m plus n constraints and solve, we get an integer. So this is one way to go about things. Okay, so you could say I know what my constraints are and I know what the variables are. So I can try to see all possible sets of like how do I take m constraints and how do you solve this? Okay. So it turns out for some very special cases like matching, you can actually do this. Okay, yeah. No. Oh, right. So this is a very interesting point. I should mention this. Okay. So note that. So this is often one of the reasons linear programming is a very powerful technique. Is that the program itself is independent of the weights. The W's show up only in the objective. Okay. They don't show up at all in the constraints. And one nice implication of this is that solving the weighted version of this problem, where w's are arbitrary real numbers, is as easy or difficult as solving just like 0, 1 weights. Okay. Like if you remember, using the flow formulation, you could solve this problem with 0, 1 weights. Okay. Like you had this source, you had this sink that you would put, and if these weights were 0 or 1, you could actually solve this by just using the max flow. Okay. But for that formulation, it was very important that those weights were 0 or 1. Okay. But for this formulation, the weights don't matter at all. Okay, for this way of solving. Okay, so in some sense, using the linear programming approach means that the weighted problem is as easy or difficult to solve as as this 0, 1 weights problem. Okay, so this is a nice thing about No, right? So in this case, there is nothing. Yeah, so you could even solve the. Yeah, you're just giving me more interesting things to say. Right? So you could solve any problem now, right? So you could solve a minimization problem. You could solve. You can have like half weights positive, half weights negative. So maybe you want to pick some edges, not pick some other edges. You could solve that problem as well. It doesn't matter. So the only place this is the only way you're constraining this to be a matching is in this. Okay, so so that is the nice. That's one of the cool things about linear programming. That often the weighted problems are messy by combinatorial means, and linear programs just give I mean, if they work for any weights, they work for all weights. So yeah, that's a good point. Any other? Okay, so that's right. And now to prove that you have that you only have integer corner points, one way to do this is via what is called total unimodality. So I'll just explain what this means. This is kind of a clever proof. You will find it online, but I don't think it provides as much intuition. And it's one of these proofs that doesn't generalize to other problems. So I'll just outline this, but we'll do a different proof. So what this means is, so for certain problems, turns out you can actually stare at the constraints, okay, and you can argue. So right, so if you use this observation, okay, so the claim is take any m of the 2n plus 2n constraints then the intersection point has only 0, 1. Okay, and so actually, yeah, I should be a little bit more precise. It turns out that it has only 0 or plus minus 1 values, and you can't have minus 1 because you are in the feasible set. Okay, so that's why it's 0, 1. So, alright, so how is this proved? So this is proved by showing that in some sense you look at all the constraints as a matrix. Okay? So let's take a small example here. Okay, so let's take a graph of this kind. So it has 3 edges and 2 vertices on each side. So you have 1, 2. So you have so your variables are x11, x12, x3. Your constraints in this case would just be these two have to sum up to at least to 1. This guy is 1 and so on. So your constraints would be like yeah. The point I'm trying to make is that you can write down the constraints as some kind of a clean matrix. Right, so let me write this down. So we have 2 kinds of constraints. I'll probably write 2 matrices, but remember that when we are looking at the intersection, we all inequalities because we are looking at the intersection of these planes, right? And each plane is actually just an equality. Okay. So maybe I'll skip that step and I'll write the inequalities also as just some. So you have right. So I will have the variables as the columns x11, x12, x22. Okay, and so the first inequality, which says that x11 is bigger than or equal to 0, will be something like this. And you will have the corresponding inequality will be this is bigger than or equal to 0. Right? This is like saying x11 is bigger than or equal to 0. If you have x11 less than or equal to 1, then you would have something like this. So, and I'm being a little informal here because different, I mean, it's not like, yeah. I'm just writing down the constraints in the matrix, the coefficients of the constraints as a matrix. Not trying to be very precise. And for a constraint that says x11 plus x12 equals 1, then this will have like 1, 1, 0, and this thing will be equal. and so on. Okay. So each constraints, all I'm trying to show is that there is this matrix that has m columns, okay, each corresponding to one of the variables, and it has 2m plus 2n rows, each corresponding to one of the constraints. Okay. So let's consider this matrix, and let's give it a name. Let's call it capital M. Okay. So capital M is this matrix that has these. The reason I'm saying this is that now what does it mean to take m of these constraints and find the intersection point in terms of this matrix? Like this is a matrix that has one row for every constraint. Yeah? Columns or rows? I mean all sorry?
And linearly independent rows.
Yeah, so any corner point is basically m of these inequalities, right? So you basically say, oh, okay, I will pick m different rows, and so these would have some 0, 1 values, and I will solve the corresponding equality. Okay, so let me write this down. So any corner point can be obtained by solving a linear system. So this is actually an easy thing. Linear system. A times maybe I should not just go like this. So B times X equals, where B comprises precisely n rows of capital, and Z is the corresponding alpha, is the corresponding is the IS of the corresponding constraint. Okay. So any corner point, okay, it's obtained by solving m of these equalities. Okay, so each constraint corresponds to one row. So picking m constraints like picking m rows, and you solve that system of equations that you get by picking those rows. And now this is an m by m system, so you will hopefully have a unique solution. Okay, unless they were linearly independent, in which case this is not a corner point. So, right, so I will pause here because this, although this is simple, this is any place where there's notation, people always take different amount of time to pass. So I will pause here for this. So any questions? Yeah.
Go back to the formulation of M. So what is those things you wrote down? Is this a particular solution that generated this particular M? So when you wrote down some zeros and
No,
ones?
the m is generated only using the constraints. Okay, so this was corresponding to the constraint that x11 less than equal to 1. And this guy was corresponding to the constraints that x11 plus x12 equals 1. Okay, that's why these are these are what I'm calling the z values. Okay, so these are the right hand sides of these corresponding inequalities. I'm just writing them. It's just corresponding to every constraint. I'm writing one row. And
Why does x11 greater equals 0 imply that x12 is equal to 0?
yeah, I mean it will end up implying, but we are in this example, right? But when we write the matrix, we are just writing down whatever the constraints are. We are not thinking ahead and actually solving for the thing, right? So this has nothing to do with the solutions. This matrix is just from the constraints. Okay. There is just some matrix that I'm obtaining from the constraint, and you could even skip this step if you don't want. It's just that I feel that conceptually it's nice to have this full matrix. We are just thinking of m of the columns, m of the rows of this matrix. You can just skip this step and say, if any corner point is basically m equations, and each equation is of a certain kind. It has some coefficient. I mean, I can just look at this matrix B, right? Like each equation is just it's a linear set of equations in x11, x12, and x22. So I could just look at those coefficients. But it's just that it's more convenient to think of m of the rows of this matrix, because they're only a small number. Alright? So, yeah.
So in that, in the next line, the x is specifically a solution to that equation, or how does that represent?
Yeah, so the small x is, I'm using it always as a short form for all the x's. So small x is, in this case, it would be x11, x12, x22. Yeah, yeah. So always small x is a vector solution.
So we have to show that all of this x is 0.
Right. Each xij will be 0 or 1. Okay. So this is what you have to end up showing. So the proof of this thing, so I won't show this method because as you can see it's a bit notation heavy. So basically it involves showing that determinant of B is always plus or minus 1. Okay? Sorry, it's either 0 or plus minus 1. Okay? So the idea behind this whole total unimodularity approach is that the claim then would be, so this part turns out to be somewhat easy. If you guys think about it, you'll be able to come up with this. Okay, so it's just how B is defined. But the main difficulty turns out to be in showing that the determinant of this matrix B is always 0 or plus minus 1. Okay? And this is a nice fact because if your determinant is 0 or plus minus 1, then you know that x can be obtained by, if you guys remember your linear algebra, so each coordinate of x can be obtained by determinant of, like if you want to solve a linear system ax equals b, right? So what you would do is, to obtain the ith coordinate of x, you would take the determinant of the whole matrix apart from this. So this is called the principal minor, if you guys remember. Okay, so trust me, but so this would turn out to be something like this is some det of b bar divided by determinant of b. Okay, so each xij you can write it like this. Okay, turns out. And now this is obviously an integer, and if you can show that this is plus minus 1, then you would have shown that each xij is an integer. Okay. And this is the idea behind this total unimodularity approach. Okay. So we won't go into this, but this is something people use all the time. Actually, and if you take this structured prediction class that that Vivek offers, so some of these NLP formulations turn out to have this total unimodularity property and so on. Okay, so this shows up a lot. One of the simplest cases, in fact, I think this is probably the case in which it originated, is this setting of matching. Okay, so yeah. But the whole point is in showing that you take that M matrix and you take any take the determinant formed by any M of the rows, and that would be a 0 plus minus 1. That would be either 0 or plus minus 1. Okay. So it turns out, yeah, so as I was saying, it's a little tricky to prove. It's a short proof, but a bit tricky. Okay, so let's not go into that. Yeah. So that just means that the determinant is non-zero, right? But, they're not orthogonal. No. So I guess you're asking if they're orthogonal. No, they're not. That would be one case in which the determinant would be 1, but yeah, it does. Oh, would be -1. Yeah, you can come up with graphs and play with them. You'll find examples where it's -1 as well. Yeah, I mean, determinant has all these weird signs, right? So, okay, so this is one proof. Okay, so this is probably one of the early proofs. But a better proof, in my opinion, is actually using a better. This is now a proof still of the same fact. We still want to prove this theorem that all the corner points are integral. Okay. So the question is, you could ask yourself, what is a corner point, right? So I want to come up with a characterization of a corner point. Can you guys think of, like intuitively, suppose somebody gives you these like sets of equations, and what is a corner point? One way is to say you solve m of these things and you solve m of these things, and the point that you end up with is a corner point. I mean, if it's not feasible, it's not, but otherwise it is a corner point. That's what you can say, right? But is there any better way you can characterize a corner point? Anything you can think of that involves perturbations? Like, what is nice about an interior point? Interior. If you are in a feasible region and you are kind of in the interior, right? Interior, if you perturb, you stay within. Right? Now, if you're at a corner point, you could imagine that, okay, there are some directions in which you perturb and you get out. Right? But the important thing, which turns out to be very crucial, is that if you take a corner point, okay, and you take any perturbation direction z, okay, exactly one of perturbing by z and perturbing by minus z, or at most one of perturbing by z and perturbing by minus z remains in the polynomial. If you think of like infinitesimal perturbations, so let me write this down. So if you are a corner point like this, okay, so then for any perturbation direction z, so U is a corner point. If it's true, for any perturbation direction z at most one of U plus z is in the feasible set. Okay, and this is a very powerful characterization if you think about it, because we are saying that if you take any direction, at most one of these two is happening. Okay? Like in this case, like a point here has two directions. Has one direction z, for which both z and minus z are feasible. Okay. So that's why this point is not a corner point. But if you take this guy, then for any z, if you move a little bit along this, minus z would not be in this. Okay. So this turns out to be an equivalent characterization of corner points. Okay. And geometrically, this is a very clean fact. All right. So what this means is that, yeah.
That direction has any constraint because what if we do like this?
Yeah, so in that case, neither of them would be feasible. So as I was saying, at most one of u plus z and u minus z are feasible. Okay, so it could be that neither of them. So you're asking, I guess, if you have z like this, right?
Yes.
So in this case, neither of them are in this, but still at most one of these two directions, these two perturbations is in, right? So that's the very cool thing about corner points. Okay. So now, what this tells me is that given u, okay, if I need to show that u is not a corner point, all I've got to do is come up with some direction z such that u plus c and u minus z are both feasible. Okay, so given u, if we need to show that u is not a corner point, then it suffices to exhibit z such that z not equal to 0, of course. Okay. And this is very clean, right? So now, yeah. So what I will show is that if you take any fractional point, okay, there's always some z which is non-zero. So u plus z and u minus z are both in the field. Okay. And this will prove what we want because then it shows that every corner point has to be in use. Okay. Because for any fractional point, you can move around and still stay feasible. Therefore, the only points where that cannot happen are integer points. So this is an indirect way of showing that all corner points are actually integers. So the proof 2 is based on let u be any feasible non-integral point satisfying star remember star is our set of equations. Then there exists z such that u plus u and u minus z both satisfy c. Z not equal. So this turns out to be what we do. Okay. And yeah, so does everyone understand the proof method? I think the proof method is more important than the actual proof itself. Okay, so this is a clean idea. Alright, so now you can try to prove this. Okay, so now you can try to say, let's take any feasible solution. Okay, so this is given by a vector u, right? So this is, you have uij for every edge ij. U is like the x before. So you have these uij's. So you have the graph. And you have this uij. Now some of them will be integral, some of them will not be integral. But we know that at least one is non-integral. Okay, that's how we define that U is not integral. So let's assume, so let's only look at, so let us draw. So this was the original solution, Uij. So this had values for, this had Uij values for each edge. I'm going to draw only these special edges. So let's call E prime a set of all edges ij such that Uij is strictly fractional. There have to be at least some edges like this, right? So these are again a subset of the edges, and there is some Uij here. There may be others. Okay, so this looks something like this. So note that there could be other edges out of these guys. It's just that those are either 0 or 1. Alright. So this is just the graph with the edges E prime drawn. Right. So one trivial observation. If I take any vertex onto which there is such an edge, okay, with Uij, can there be any one? Can you have a Uij that is 1 that is connected to this guy? Okay. What I mean is, like if I look back, the set of all Uij, right? And if this, yeah, so suppose I take this edge, so I is here, J is here. Can there be any Uij that is equal to 1 that is connected to also to the same I? So the answer is that you cannot, and the reason is that we know that because U is a feasible solution, all of these sum up to 1. Okay, so all the edges for every I sum up to 1. So if there is one edge whose value is strictly more than 0, you can't have another edge that's equal to 1, which is sum of the value. So what this means is that if you look at these edges, all the other edges that go out of the vertices that are involved here, they're all zeros. So you can't have any like one edges going out of these guys. So now let's look at a case in which you have a picture like this. If you had a picture like this, now I want to claim that there is some direction in which I can move there's some z. Okay, z is just a change of u's, right? So u is one solution. I want to show that u can be perturbed. Okay. So that I still remain within the physics. Now, if you had a picture like this, what would be a perturbation z that you might want to come out? In particular, like if you had a lone edge hanging out here, right? Can you use this to say that there is some perturbation z so that you can do both sides and still be feasible? So, yeah, what are you saying?
Because if you have the contribution, the opposite direction can be feasible. Like if you add something small to the field, which is
Yeah. So no. So I guess what I would maybe I'll ask a different question. Okay. So I guess the first question to ask is, if I define U this E prime a set of all edges where 0 less than Uij less than 1, can I end up with a situation like this where there's a lone edge? First. Why do you say no?
Since it's less than 1, you can need exactly what between every, or on every I or j.
Exactly. Okay, so our constraint said that for every for this vertex, sum of everybody had to be, sum of all the edges connected to this had to be equal to 1. Okay, sum of all the edge weights connected to this. had to be equal to 1. Right? So you can't have a lone edge here with values strictly between 0 and 1. Okay? So everybody has at least degree 2 in this graph. Okay? So for the same reason, this guy can't have just one edge. Okay? Because all the other edges are 0, and you can't have just, this plus all the values cannot be equal to 1. So, simple observation about this E prime graph is that every vertex has degree at least. Okay, so this E prime graph essentially looks something like this. So maybe it has so it's a graph where every vertex has degree at least 2. Okay. Is that clear? No? Which part is not clear?
I know why every vertex has degree less than 2.
Oh, at least 2. Okay. So in particular, I want to say that it cannot have degree 1. Okay. Because these are discrete edges, right? I'm looking at all ij where 0 less than uij less than 1. And I'm looking at just these set of edges. My claim is that among these set of edges, if I just look at the set of edges, then for every vertex, either there is no edge incident to it, okay, in which case we're fine, or there are at least 2 edges incident to it. Okay, so in particular, there cannot be precisely one edge incident to any vertex. So maybe I should say every vertex has degree at least 2 or 0. So equal. I'm only looking at things that have at least 2. So, and the reason is that if you had exactly one edge with value uij between 0 and 1, then we know that all the other edges have either 0 or 1. So you can't have a 1, as I just argued. Others have to be 0. So if everybody else is 0, then the sum of all the uij's going out of this vertex will not be equal to 1. But that was one of our constraints. Right? Like one of our feasibility constraints was that for every I, sum of xij was equal to 1. Okay? This constraint would be 1. So that's the reason. So this is, I'll pause here so that if others have a question, you can ask them. Right. Okay, so now it turns out you have these E primes are graphs in which every edge either has degree 0 or it has degree at least 2. Okay. And the nice thing about such graphs, maybe you've seen this problem before, I don't know if you've explicitly seen this, is that any such graph must have a cycle. Okay? Because it's, and the way to prove it is actually very simple. You start with any vertex that has degree non-zero. You know there's one edge out of it, take that edge. Okay. And so you know that its degree is now at least 2. This guy's degree is at least 2. Okay. Take that edge out. Okay. And if you hit something that you've already hit before, then you've found a cycle. Okay. Otherwise, you keep reaching things that you've never reached, in which case your degree was 1, there has to be another edge out. Again, your degree is 1, so there's another edge out. So worst case, you'll take n steps, but you will still find the cycle. Okay. So this is an easy way of trying. Okay, so this is simple exercise. Is any such graph as a cycle. And that means if there is a cycle using only the edges of E prime. Okay. So remember, E prime were defined to be the set of edges where Uij was strictly between 0 and 1. Okay. Now I'm now saying there's now a cycle that involves only such edges. Okay. So let me now give example of when such a situation might happen. You have point 3, you have point 7, and maybe you have 0.2. Too many edges. So let's keep it a little bit short. And this one with point 6. So, I mean, all I'm saying is you have a cycle where all edges have weights strictly less than 1. And now I claim that you can find a z pretty easily. Okay, where you can perturb these weights in two different directions and still be feasible. Right? So why would you get? I mean, how would you come up with the perturbation of this kind? So if you had weights like this. So the nice thing about a cycle is that everybody has degree exactly 2. Right? So what you could do is, what if I start off by going, so let's say I add plus delta to this edge, minus delta to this edge, plus delta to this edge, and minus delta. Okay, so I just move in the cycle and add delta to alternate things and subtract delta from one. Now, because this is a cycle, you can verify that for every vertex, the sum of these things remain, sum of the edges connected to it stays exactly the same. Okay, and you've got to, so it stays exactly the same. And if delta is small enough, okay, then you know that each of these weights was strictly less than 1. Right? So in this example, if delta was, let's say, less than 0.1, everything will still continue to lie between 0 and 1. Because they were bounded away from 1 to start with. Okay, so if you added a little bit, there is still some slack. Okay. So what you can argue is that this still remains feasible. And this is basically the proof. Okay, so I won't spend too much time on this, but this is right. So you find the cycle, and so for small enough delta, this will still be a feasible. And delta could be both positive and negative. And this is exactly the perturbation that we want to the solution. Okay. And this gives the perturbation we want to the solution. Okay. So yeah. Given that we are short of time, I think I will. Maybe I'll take questions on this thing offline. But this is the main idea, that you find a cycle in this set of edges that are strictly between 0 and 1. And once you do that, you're done, because now you can increment one edge slightly, the alternate edge you decrement it slightly. long as the changes are both the same. And then all the constraints will be satisfied, and now you end up with you end up with a situation like this, where you can move the point around a little bit in two directions, and you still stay physical. And this is ideal. Yeah, and this shows that no fractional point can be a corner point. It's proved by contradiction. So, no fractional point can be. Or in other words, all corner points. So that's all right. So this is all for the example of matching, right? So for matchings, yeah, I mean, yeah. So this is often considered a simple proof. Okay, so it's you have a relatively simple proof that all fractional points. Okay, so it turns out you can mimic such an argument for flows as well. Okay. So flows, you can still show that all the corner points. So I won't again go into this formulation because we've seen this before, and I don't think that's much value. But yeah, so if you write down the constraints for flows for the maximum flow problem, turns out that that's also an integer. Okay? And a consequence of that is that this here implies that for solving flows, for finding max flow, we can simply use linear programming. So our algorithm from before was nice, but we don't really need it. Okay, so you could just use linear programming, and the optimum point, the corner point of this flow concept will always be an integer point, and so you can use this. Alright, so a couple of warnings. So it now seems like, oh, okay, maybe for many interesting problems this happens. So one unfortunate thing is that this is a very, very special phenomenon. Okay, so this fact of all the corners being integers very rarely happens in practice. Okay, for most interesting problems, if you write down the natural linear programming relaxation, its corners will not all be integers. Okay, so that's so that's an unfortunate fact. Okay, so polytopes usually have fractional corners. So I wanted to illustrate an example where you get fractional corners, but they're not terrible. Okay, so we might not be able to finish this, but let's start with it anyway. Okay. So the problem we have seen before. Okay, so I was trying to remember where exactly we saw this, but I couldn't quite place it. Okay, so I think we saw this when we were looking at 3D algorithms. I'm not sure. Okay, so the problem is the following. Okay, so you're given an undirected graph. This is just think of any simple graph. And you want to, so maybe I motivated this being this like the policeman problem, right? Like you have a bunch of roads, and you are allowed to place policemen at intersections. You want to place the fewest number so that they can monitor every road. Okay, so this is one way of phrasing this. Okay, so this is also called the vertex cover problem. Okay, so you are given some undirected graph, and you want to find a set of nodes. So once you pick this node, these edges are all covered. Okay, and maybe you pick this. So you have covered this edge and this edge. So maybe I'm doing a bad job, but if you pick this and this, now you can be sure that for every edge, at least one of the vertices is connected to that edge. This way. If you think of edges as roads, then all roads are being monitored. So that's Yeah, so this is the problem, and your goal is to place as few nodes as possible. Okay, so find a small set of nodes. So your optimization problem is find the smallest number so that all edges are monitored. So firstly, how would you come up with a linear programming formulation? And remember, usually when you want to come up with a linear programming formulation, you first come up with any optimization formulation, and then you replace the constraints by replace these discrete constraints by just 0 less than x less than 1. So this is how you would ordinarily come up. So how would you come up with an optimization? So you've got to ask yourself, what are the variables, what are the constraints, what's the objective? Yeah?
Variable will be whether a vertex is to be chosen or not.
Okay, so you have variables xu. This is vertex chosen or not. Yeah. Okay, this is 0, 1. What are the constraints? And this is natural, right? Because you want to choose a subset of the vertices. So you want to keep a variable for whether one vertex is chosen. Now, what is the constraint we want? Yeah.
For each edge, you just add up the vertices that it's adjacent to, and that's quantity has to be greater than
Yeah. So you would say that for all the constraints, for all edges ij, xi plus xj is a and right, and this is it, right? So and you want to minimize, of course, the sum of this is the number of things that you pick. So this is very simple objective, and now you can make it into a linear program by doing the same trick we did before. You can say instead of requiring these to be discrete 0, 1, you could say I just have 0 less than or equal to x. By the way, this process of going from optimization problem that is that has these integer constraints and an optimization problem that's actually a linear program. This is called relaxing. Okay, so it's like you are relaxing these integer constraints of xu in 0, 1 to 0 less than equal to xu. It's called relaxing because the original solutions are still solutions. So these are, in some sense, the second constraint is a weaker constraint than the first one. First one means that you have to be one of these two. Second one means you can be anywhere else. So that's why this process is called relaxing. All right. So this is the linear program, and now, yeah, let me show you a bad corner. Okay, and then we can end with that, and next time you can see how to fix this. Okay. So these are all the constraints. Right? So if you had, let's take a very simple graph in which you have UVW, and this is a triangle. Now what are your constraints? You get 0 less than for xu, so you have these constraints, xw, these are all less than 1, and xu plus xv is Now, what is an example of bad corner? Anyone else? you seem to be saying the right answer, hopefully. Yeah, so as you would likely to say also, if you have all xu's equals half, okay, that would, this would be a bad point. Right? So xu equals xp equals xw equals half. And you can verify that this is a corner because if you solve these three equations, like these are three planes, and the solution to this is exactly this point, half, half, half. And that's feasible. Now, what this would mean is that the minimum is actually 3 by 2. Okay. So if you think about it, you can't have a solution to this problem without picking two of these things. So the true optimum value for the combinatorial problem has objective value 2 because you have to pick at least a set of size 2 to cover all the edges. But your linear program is telling you that the optimum is 3 by 2. So this is what is called a gap. This is what is called the integrality gap. Okay, but we will show how in this case, okay, you get a solution that's kind of bad, but maybe it's not too bad. So this is what we'll see next time.